5.4 is on oxidation and reduction. And oxidation and reduction are two separate types of reactions that always occur together, to the point that we often just mash the two words together and say redox. All right? Now, redox reactions refer to movement, basically deal with movement of electrons. So, when we talk about an oxidation reaction means a loss of electrons. And a reduction reaction is a gain of electrons, right? Now, I say they always occur together. When we have an oxidation reaction, where do the electrons go? They go to supply the reduction. Where does the reduction reaction get its electrons? They come from the oxidation. So they always occur together. Here's an example of a redox reaction. I should say this is an inorganic redox reaction. All right, 4Fe plus 3O2 back to form 2Fe2O3. All right, let's look at what's going on in this. Okay, iron has gone from its elemental form to being in a compound. Now, if we look at this, a compound in its elemental form has a charge of 0. By the way, I'm kind of dancing around in teaching this, or in explaining it this way, because your book doesn't go into this, teaching this concept called oxidation numbers. We're really going to talk about charges, or what we're going to talk about today are our charges. Really, what we're actually talking about are oxidation numbers, which are a formal system of assigning charges, or of assigning these things and of keeping track of what's going on in an oxidation reaction. But anyway, something in its elemental form has a charge of 0. Right, now, if we go to our periodic table and we look, we know that oxygen is always going to be a -2 charge. And we can sort of work backwards in this, and we can know that this iron is a +3 charge. So what's happened in this? Iron has gone from 0 to +3. Oxygen's gone from 0 to -2. Right? What has to happen for iron to go from 0 to +3? It loses electrons. What has to happen for oxygen to go from 0 to -2? It has to gain electrons. So we can see in this that oxygen, or that I should say that iron, has been oxidized. And oxygen has been reduced. Right? Iron has lost electrons, oxygen has gained electrons. Oh, but by the way, also in a redox reaction, the iron was what caused the oxygen to be reduced. So the iron is the reducing agent. The oxygen is what caused the iron to be oxidized, so the oxygen is the oxidizing agent. Okay? Now, I realize this is a lot to keep track of. There are a couple mnemonics that you can use to remember what way how the electrons go. The one that I learned and that I always use and teach is oil rig. Oxidation is loss. Reduction is gain, right? So that's inorganic redox. We just keep track of our charges. We look at what's going on with it. There again, the more formal, proper way to do this is to look at oxidation numbers, but for anything we would do, they're going to be interchangeable. All right. Now, let's talk about organic redox. Okay. In an organic oxidation, we increase our number of oxygens and or increase bonds to oxygen and or remove hydrogen. Right, what do I mean by that? Let's say that I have this is ethanol. This is a primary alcohol. I oxidize it. By the way, this is not inconsistent with what we learned above. It's just a more generalized telling of it. But let's say we oxidize it. Now, how do we oxidize it? Well, to do what I'm showing, we would use something like pyridinium chlorochromate, PCC it's called, or some other reagents like desmartin periodinane is one of them. But in any case, and those are the things that get reduced in this oxidation. But anyway, if we oxidize this, though, we oxidize it to this. So we go from a primary alcohol to an aldehyde. We could oxidize it further, use something like chromic acids, kind of the old standby. This will actually just happen kind of on its own over time with oxygen, but whatever oxidizing agent we use, we're going to go to this, to a carboxylic acid. Right, so what's happened here? When we go from here to here, oh, I messed this up, sorry. That should be a hydrogen there, not an OH. So this is an aldehyde, this is a carboxylic acid. All right, let's look at what happened here. We got rid of a hydrogen, so we did that. We increased the bonds to this oxygen. To go from here to here, we added another oxygen. All right, now, if I have, let's say, a secondary alcohol, and I oxidize it, secondary alcohols get oxidized to ketones, right? We've gotten rid of a hydrogen, we've double bonded to this oxygen. By the way, tertiary alcohols cannot be oxidized. Okay. Now let's talk about organic reductions. So if I have let's say a carboxylic acid, I could reduce this. Actually, let me give you a definition first. Organic reduction, we add H and or remove O. All right. Let's reduce this. What do we use to reduce it? I'm actually not sure what reducing agent would get us to the aldehyde here. I'm sure there is one. I'm just not well versed enough to do it, to tell you what it is off the top of my head. But that gets us to the aldehyde. Removed an oxygen there. Let's reduce it again. We could do this one with something like sodium borohydride, lithium aluminum hydride, something like that. Alright, what have we done there? We've removed, or we've added hydrogen. Okay. Now, if I take something like a ketone, and I reduce it there again with something like, we don't really care what we're using here, but sodium borohydride, anything along those lines. I'm going to get an alcohol. By the way, this is not a formal organic chemistry course. Chem 130 is not a formal organic chemistry course. So, if you know of other reduction options, or when I say that things can't be reduced, and if you know of ways to reduce things that I've said can't be reduced, just don't worry about those. This is the level where we need to know them for this course. But basically, that's redox reactions in a nutshell.